Okay, welcome back, everybody. It is a great pleasure to have Tim Roughgarden as our keynote speaker in this workshop. Well, Tim actually needs really no introduction, and he is one of the pioneers of this subfield of algorithmic game theory. Together with Eva, they co-authored one of the first papers on selfish routing, and his results have already been referenced quite a few times already during this workshop. So today he's going to talk to us about barriers to near optimal equilibrium.
Alright, thank you, PECASE. Alright, so good morning, everyone. Thanks for waking up early and showing up. Thanks also to the organizers for sort of both envisioning this event and getting together such a great group of people. When I first started working on the Prize of Anarchy, I was a second-year grad student. So fast forwarding 20 years, it's like blowing my mind to see that, all this time later, there's still such a, vibrant community of super smart people working on these topics. It's really cool. What I wanted to tell you about today is one of my most recent papers on the Prize of Anarchy. That said, it's not particularly recent. It's from 2014. But still, it seemed like a good opportunity to sort of remind people of this paper's existence, which presents a pretty general complexity theoretic methodology for proving lower bounds on the Prize of Anarchy in many different classes of games. So the starting point for this work was trying to understand whether there were senses in which game theoretic equilibria, like say Nash equilibria, are fundamentally more powerful than efficient algorithms, polynomial time algorithms. That is, can equilibria do things in some sense that efficient algorithms cannot? And in some sense, kind of most of us already have a belief about the answer to that question. We believe the answer is yes. Because recall, that computing a Nash equilibrium, say a mixed Nash equilibrium of a bimatrix game, that's a PPAD complete computational problem. Most of us believe PPAD does not collapse to P. So in that sense, a Nash equilibrium is doing something, is computing something, not computable by polynomial time algorithms. So in some sense, the answer is yes. But what about for optimization problems of the like that we think about in Prize of Anarchy studies? So for an NP-hard optimization problem, do we expect Nash equilibria to be able to accomplish things that efficient algorithms or say low-cost communication protocols could not? Okay, so that was sort of the motivating question. And I want to show you a number of senses in which the answer is no, in which equilibria are not more powerful than polynomial time algorithms or polynomial cost communication protocols. So what we're going to see a number of results which basically say the types of lower bounds that we have a lot of experience proving for, say, efficient algorithms, like hardness of approximation results, those will actually also apply equally well to Nash equilibria of games. Okay, so that'll be sort of the high-level meta theme to look out for. The sort of moral reason, which will pervade this talk about why that's true, is because Nash equilibria, while maybe not polynomial time computable, they still somehow have low enough complexity that they can't do things like solve NP-hard problems. And the sort of, the two principles which really sort of are going to drive all of the results are we're going to be looking at equilibria that are guaranteed to exist. So think about like pure equilibria in congestion games or mixed equilibria in finite games. So that's the first thing that will drive the results. And the second thing is going to be the efficient verifiability of an equilibrium. So if I write down an alleged equilibrium and hand it to you on a silver platter, it should be easy to check whether or not indeed all the best response conditions hold. Okay, so this is just sort of the high-level stuff to look out for. The rest of the talk will be more concrete, but these are going to be the themes that you're going to see. All right, so I want to sort of demonstrate this in two different case studies. So the first one for congestion games, or really more specifically, I'll focus on routing games and show you how hardness results for the underlying optimization problem translate to conditional lower bounds on the Prize of Anarchy. And then I want to talk some about combinatorial options and the Prize of Anarchy of simple mechanisms, and there we'll see how communication complexity lower bounds, again, translate to lower bounds on the Prize of Anarchy for simple mechanisms. All right, so to this audience, especially sort of on the third day of the workshop, I don't think I had to say much about routing and congestion games, so let me just be quick. So think of a routing game. You have a directed network, you have an origin and destination. Maybe different players have different origins and destinations. I'm going to be looking at the atomic case. So we're going to have a finite number of players. They're going to be unweighted, so everybody controlling one unit of flow. And it's going to be unsplittable, so each player has to route that flow on a single path. Each edge, of course, is labeled with a cost function describing the cost of traffic on that edge as a function of the number of players who are using it. So in this particular example, there's a unique Nash equilibrium. Both players have a dominant strategy to take the zigzag path. As a result, they're both going to use paths that have cost 14. The joint cost is going to be 28. If you could coordinate the players, you instead would split them on these two different two-hop paths. One player would still have cost 14, the other's cost would drop to 10. So the joint cost would drop to 24. Okay? And the price of anarchy, as you all know, is just the ratio between these two quantities, which in this particular network would be 7/6. And it's important to remember that the price of anarchy is a worst-case notion. So in games with multiple equilibria, which frankly is most games, the price of anarchy is governed by the worst of all of the equilibria. Indeed, the Koutsoubias-Papavichou paper from 20 years ago, the title of that paper is Worst-Case Equilibria. Right? So it's the worst case in the same sense here. Obviously, the closer the price of anarchy is to 1, the better. Okay, that sort of is tighter and tighter bounds on the worst-case inefficiency of equilibria in your class of games. All right, so something which I think was clear certainly in Georgios' talk yesterday, if not earlier, is that to say interesting things about the price of anarchy in routing games, it's very important that you parameterize by the class of allowable edge cost functions. If you allow arbitrary cost functions, it can be anything, there's nothing interesting to say about the price of anarchy. It can be unbounded. This is true even in the relatively simple case of a non-atomic routing game where you have an infinite population of infinitesimally small players, and even just with polynomial cost functions if you allow the degree bound to go to infinity. Okay? So whenever we talk about the price of anarchy of congestion games, we always need to have in mind what class of edge cost functions are we talking about. And so we need to restrict them. A strong restriction would be, say, affine cost functions. A more relaxed assumption would be, say, bounded degree polynomials with non-negative coefficients, where the degree is, whatever you want. Okay, something bigger than 1. All right. So we always discuss the price of anarchy parameterized by the family of cost functions. And as you saw in Georgios' keynote lecture yesterday, at this point for congestion games, we have sort of a very satisfying and exact understanding of what is the price of anarchy. Okay, so we have a lot of results of this form, but let me single out this one by Martin and his collaborators from a while ago. An important paper. So they show that in unweighted congestion games with bounded degree polynomial cost functions, degree at most d, non-negative coefficients, they give an exact expression for what is the worst case price of anarchy in that family of games. Okay, and the good news is it's finite, it's constant for any constant d. The bad news is that it is blowing up exponentially in the degree bound. Okay, and it grows roughly as d over log d raised to the d, or d plus 1. Okay. And one of the cool things about this paper is they needed to introduce both new upper bounds and new lower bounds. So the new upper bounds were actually quite important in the development of the theory of smooth games. That's not what I'm talking about today. I want to focus more on the lower bounds. And as far as how they prove their lower bounds, what's the way you would think they would prove a lower bound in the price of anarchy, namely by an explicit construction. So they simply wrote down a routing game, told you what the cost functions were, exhibited the equilibrium, which has costs very far from optimal. Okay? And it's a clever sort of construction that accomplishes that. This is just sort of one small sub-piece of the construction that they present. Okay? All right, so that's an example of a class of games I want to talk about, the type of lower bound that I want to generate. And I mentioned that the point of this talk is going to be a methodology for translating hardness of approximation results, so lower bounds on efficient algorithms, to lower bounds in the price of anarchy. Okay, so I've told you already what games I care about, congestion games with polynomial cost functions. What is the optimization problem that's going to be relevant, that I want to prove hardness of approximation for? Okay. Well, that's just going to be the denominator of the price of anarchy, okay, the optimal outcome. So formally, the computational problem is I give you a description of a routing game, say with polynomial coefficients, so I just describe the network, I tell you the coefficients of all of the polynomials, and I want you to compute an outcome, again, a choice of path for each player from its origin to its destination, that minimizes the joint cost. So like in that simple network a couple slides ago, we want an algorithm that computes that routing that has cost 24. Okay. So that's a well-defined cost minimization problem. Now, the way we want to think about sort of the connection here is we want to think about any near-optimal equilibrium, right? So something where that ratio is not too big, at most alpha. We can think of that equilibrium as in some sense approximately solving this optimization problem. And in particular, if the price of anarchy is small, if even the worst case equilibrium is is close to optimum, then in fact every equilibrium of this game constitutes an approximate solution to this optimization problem. Okay, so that's going to be the connection we're going to be exploiting. All right, so let me actually sort of state the first main result. Maybe you might want to start by reading the bottom sentence before reading the actual technical statement. So again, the point of this theorem is to translate hardness of approximation results for the optimization problem I just showed you, cost minimization, into lower bounds on the price of anarchy, subject to a complexity assumption. Okay? So specifically, think about a family of routing games. Think about your favorite set of cost functions, like degree d-bounded polynomials. Suppose two things are true. Okay? First, suppose you have a hardness of approximation result, meaning there's some factor alpha where it's NP hard to decide whether the cost is at most C star or bigger than alpha times C star. Okay? So that's the hardness of approximation assumption. Furthermore, assume that NP is not equal to co-NP. It's a stronger assumption than P not equal to NP, but not much stronger. Almost everybody believes that this is true. Okay? If both of these two things are true, then you can conclude, in fact, that the worst case price of anarchy in routing games with this class of cost functions is at least this exact same approximation threshold alpha. Okay. So that's the first result. I think I'm going to tell you first about the proof, which just takes up two slides, and then I'll show you an application. Okay. And so again, I want to point out, when we talked about the lower bound on the price of anarchy earlier, I said, it was proved the way you'd expect it to be proved by an explicit construction. And as it happens, a pretty ingenious explicit construction. And so, the point here is that this is a very, very different way of generating lower bounds on the price of anarchy. In particular, this proof will not offer a specific congestion game that has a large price of anarchy. You could probably derive one from the proof, but the proof does not explicitly do that. Rather, it just stands on the shoulder of complexity theory. It builds on impossibility results for algorithms and says equally good impossibility results must existentially also hold for equilibria. Okay? All right, so maybe this seems a little mysterious. Let me show you the proof. I think that'll demystify it a little bit. So I mentioned how what's really going to be driving the results in this talk are two properties of equilibria: guaranteed existence and efficient verifiability. Okay? So we're looking at routing games, so let's talk about pure equilibria. Okay? And remember, we're proving lower bounds. So a lower bound on pure equilibria is an only stronger result than a lower bound on the price of anarchy for any more permissive equilibrium class. Okay? All right, so pure equilibria, as I think you all know, pure equilibria are guaranteed to exist in atomic routing games. This is the classic argument of Bob Rosendahl from 1973. It's a very nice potential function argument, which has been alluded to earlier this week. And then we also need efficient verifiability. So suppose I handed you an alleged equilibrium of a routing game, meaning I just specify one path for each player. How hard would it be to check that it really is an equilibrium? Well, an easy exercise is to notice you could verify the best response conditions with one shortest path computation for each of the players. Okay. So it certainly is polynomial time solvable to check whether or not a given outcome is a pure Nash equilibrium of a routing game. Okay. All right, so this was slide one, and these are the two facts that we need: guaranteed existence, efficient verifiability. We have both of them for pure equilibria of atomic routing games. All right, so given these, how's the rest of the proof work? Well, kind of like every result ever in complexity theory, the proof is by contraposition. Okay? So we're going to assume that we have a too good to be true price of anarchy bound, meaning we're going to assume the price of anarchy is some number rho better than alpha, less than alpha. And then we're going to conclude that one of the assumptions is incorrect, namely we're going to conclude that NP equals co-NP. So in effect, from a too good to be true price of anarchy bound, I need to extract a good algorithm for that cost minimization problem, a good non-deterministic algorithm for that cost minimization problem. So how do we do that? Okay, so suppose that we have a too good to be true price of anarchy bound. Price of anarchy is rho less than alpha. Consider the NP hard problem, or the problem that we're, our first assumption is that it's NP hard. Decide whether or not a given routing game has optimal cost of most C star, or at least alpha times C star. Okay. So notice this is certainly an NP problem, right? If I wanted to convince you that the optimal cost is at most C star, I could just show you an outcome with cost of most C star. You'd be like, oh yeah, you're right, the optimum can only be better, I'm convinced. It's case 2 where it's not clear how I would convince you, how I would give you a succinct and efficiently checkable certificate. How would I convince you that every single outcome has high cost? Well, the point's going to be that in the presence of a good price of anarchy bound, I can convince you that all outcomes have high cost just by showing you one equilibrium that has high cost. Okay? And that's going to give us a co-non-deterministic algorithm for this NP hard problem. All right, so in more detail, how does the non-deterministic algorithm work? Okay? We're given this routing game. We're going to guess, or a verifier will propose a pure Nash equilibrium. Okay? It doesn't matter which one, any pure Nash equilibrium. The verifier can always do this. Okay? We have guaranteed existence. Okay? That's the first lemma. And then secondly, the verifier can check the certificate. Okay? I can efficiently say, yes, prover, you did give me a description of a pure Nash equilibrium. Moreover, I, the polynomial time verifier, can compute the cost of that outcome in polynomial time. It's easy to evaluate the objective function. So that's what's happening. So the sort of certificate of being a no instance, of being either a yes or a no instance, will be this pure equilibrium. I compute the cost. And now, using the cost of this equilibrium, I can deduce whether I'm in case 1 or case 2. I can resolve this NP hard decision problem. How do I do that? Well, the first case is sort of the trivial one, which is that if the equilibrium has low cost, less than alpha times C star, the optimum can only be better. Okay? So in particular, I know we are not in case 2, we have to be in case 1. Okay, so this is the not interesting part. Okay, this is just saying there's an NP certificate for a problem that clearly has an NP certificate. Okay? How about a co-NP certificate? Meaning, how would I convince you we're in a no instance? How would I convince you that the optimal cost is really big? Well, I look at the cost of this equilibrium, and if the cost of this equilibrium is at least alpha times C star, then, by virtue of the price of anarchy being only rho, which is less than alpha by assumption, I can conclude that even the optimal outcome has to have cost at least a 1 over rho fraction of this equilibrium. Okay, at least alpha over rho times C star, which, because rho is less than alpha, this is going to be strictly bigger than C star. So I'm convinced that we can't possibly be in case 1, we have to be in case 2. Okay. So we started with an NP hard problem. I showed how to non-deterministically verify both yes instances and no instances. That puts NP intersect co-NP, which then applies the collapse of NP and co-NP. So any questions about that? I know it's not short, but it's a little bit of a mind bender. So if anything would be helpful, just feel free to ask. Okay, so that's the proof. Is this theorem good for anything? Okay, so the point of the theorem is to translate hardness of approximation results over into price of anarchy lower bounds, subject to a complexity condition. That would only be interesting if we had some hardness of approximation results to apply the theorem to. Okay, so do we? Well, you can certainly prove them for routing games. Okay? So in particular, by adapting a reduction of Chuzoi and Kana, which is for a disjoint paths problem, you can prove a hardness of approximation result that says it's NP hard to solve this cost minimization problem, to compute an optimal outcome, to approximate to within a factor better than something which is exponential in D. Okay, so a constant times the degree bound D raised to the D over 2. Okay. If you chain together this hardness of approximation results with the generic translation theorem from a couple slides ago, you immediately deduce that, assuming NP not equal to co-NP, actually the price of anarchy in routing games with bounded degree polynomials has to be exponential in D. Okay, so that follows from these two results combined. Now, on the one hand, so the bad news is this result is not as good, okay, as the explicit construction from the paper of Land et al. It's not as good in two senses. First of all, it makes a complexity assumption, NP not equal to co-NP, which we think is true, but it's an extra assumption. Secondly, the dependence of while it's an exponential lower bound, the dependence is not exact. Okay, so the constant in the exponent is not what it could be. Okay, so those are the two pieces of bad news. On the other hand, on the next slide, I'll show you that this lower bound sort of seems much more robustly true than any bound you might think of proving by an explicit construction. So what do I mean by that? Let me sort of just show you by an example. Okay, that lower bound applies not just to the price of anarchy, but also to other stuff that we've all studied in the past. So as an example, let's think about having edge tolls. Okay, so to each edge, we're now allowed to add some toll. We're going to assume that players minimize the delay experienced plus money. And the question is, can we somehow come up with clever tolls on the different edges that force all equilibria to be optimal or near optimal, at least? Okay? So in the non-atomic model, where you have an infinite population of sort of infinitesimally small players, tolls are as effective as you could possibly hope for. Okay, basically, you just charge marginal costs on all of the edges. It forces the players to internalize the congestion externality, and boom, the unique optimal solution, the unique equilibrium, excuse me, is exactly the same as the optimal solution. Okay, so you can actually recover full efficiency in the non-atomic case using so-called Pigovian tolls. What about the atomic case? Okay. Well, there we know things are not as nice. Okay, we know that tolls in general, even say with affine cost functions, tolls cannot in general force all equilibria to be optimal. Okay, but you can still ask the question, can we at least force everything to be near optimal? Like better than the price of energy bound when you don't have any tolls at all. And this exact same lower bound that I just showed with the exact same proof shows the exact same lower bound on what you could possibly achieve existentially with any set of tolls. Okay, so specifically, even if you're allowed to assign whatever tolls you want, it is still going to be the case that there will be routing games with degree d bounded polynomial cost functions so that there will be an equilibria that's exponential in d away from optimal. Okay, so it's still true, even with tolls. Why? Right, so what did I need in the last proof? I just needed, so the certificate was just going to be the equilibrium. Okay, that was going to let me certify no instances of this NP-hard problem. Here, okay, the certificate now is the equilibrium plus the tolls. Or rather, I should say the tolls and the induced equilibrium in that game. Okay, that's an equally succinct and equally checkable certificate as it was before. Okay, so the exact same lower bound is going to hold. Same thing would be true, for example, if you wanted to try to improve the price of anarchy with stackable routing. Okay, again, just the sort of leader strategy together with the induced equilibrium would constitute a short and efficiently checkable certificate. Okay. So this shows a sense in which not only is the price of anarchy exponential in D in routing games, but actually any kind of most conceivable interventions cannot bring it down to below exponential in D. Okay. And I don't know how you prove a result like that using explicit constructions. Okay. So that concludes sort of the first case study, the first part of the talk. Again, I've been sort of repeating this over and over again, let me just say it again. So, what drives the results? Guaranteed existence, efficient verifiability, and then hardness of approximation results for the underlying optimization problem become conditional lower bounds on the price of anarchy. I've showed you it for routing games. The only thing I used about routing games is that our equilibrium concept exists, and that there's efficient verifiability, and that there's a hardness of approximation of that cost minimization problem. If you have those three ingredients, the same methodology will apply. It doesn't matter anything else about your class of games. Okay, so it's quite flexible. Questions on the routing game section before I start talking a little bit about combinatorial options? Yep.
What happens if you use the price of stability concept? Can you say something?
Yeah, so good questions. The question is, what if I wanted lower bounds on the price of stability, not on the price of anarchy? So again, so here what really matters is efficient verifiability. So it is true that if you look at any equilibrium refinement notion, so any subset of Nash equilibria, where you can efficiently check membership in that subset, then this exact same lower bound will apply and will actually be stronger. Okay, so it's not just to a worse Nash equilibrium, it's to any sort of efficiently certifiable subclass of equilibria. That said, for the price of stability, that's about the best Nash equilibrium. And how would I be convinced that this equilibrium really is the best one? Okay, that's generally not efficiently verifiable. And in fact, you can even come up with examples where the price of stability beats the lower bound implied by the hardness of approximation results. Okay, so it's just not true for the price of stability. Great question. Other questions? Yeah.
So then, would it work for the equilibrium that can be reached from good solutions? I mean, instead of taking the best equilibrium, taking an equilibrium that can be reached by...
It would need to be a polynomial length path, the way I see it. So if it was something to be reached by a polynomial length best response path, you could show me the path along with the equilibrium, and that would verify it. If it's possible, right, so for example, in classes of games where it's, p-space hard to find kind of the end of the line, there I don't think this is going to work. Yeah, another good question. Any other questions? Okay. So in the second part of the talk, I want to do basically exactly the same exercise for a different problem. Okay, something, namely welfare maximization and combinatorial options, all right, which has not been as represented this week as maybe, as reflects the literature. There's a ton of work on this problem, pretty much as there is on congestion games. It's going to be a couple more technical details to get right, but I actually think the sort of, the end result, the results that we get will be even more satisfying, in my opinion, than what we just saw for routing games. All right, so let me go, so control options. So I'm sure many of you know this, but we haven't heard that much about it this week, so let me go a little bit slower. So this time what I'm going to do is I'm going to first tell you about the optimization problem I'm interested in, and only then will I tell you about the classes of games that I'm going to be thinking about. Let's just start with the optimization problem. All right, so it's going to be n bidders, or n agents, okay, and there are m items. Okay, so it's a market with n people and m items. And the feasible solutions are going to be allocations of the items to the agents, okay, with each item allocated at most once. The items are indivisible, I should say. So you either get one, you either get it, or you don't. Okay? So as an agent, I'm going to be given some subset of these m items. Okay? So bidders have preferences on which bundles of items they like more than others, and that's encoded by what's called a valuation. Okay? This is just a set function. You can think of my valuation as just a big lookup table in my head of length 2 to the m, one for each subset of items I could possibly receive, specifying the maximum amount I'd be willing to pay for that particular subset of items. Okay, so that's what I mean by evaluation, just how much you'd be willing to pay for each of the 2 to the m things you might possibly get. So that's the space of feasible solutions. What's the objective function? We're going to be looking at welfare maximization. Meaning, if we could, what we'd like to do is allocate the items to the agents to make everybody as collectively happy as possible. That is, to maximize the sum of the values for the bundles that people receive. Okay? So in a perfect world, we would love to maximize this objective function. Now, for variety's sake, let me, instead of working in a sort of Turing machine model, let's look at a multi-party computation model. Okay, so in this optimization problem, I'm going to have in mind each of these n agents. They have their valuation in their head, this lookup table of length 2 to the m. And a priori, they know nothing about other agents' valuations. Okay? And what we're after in this optimization problem is a communication protocol, meaning the players will communicate bits between them, presumably communicating information about their private valuations. And at the conclusion of the protocol, we would like it to be true that the agents have collectively computed an allocation with maximum welfare, or at least approximately maximum welfare. Okay. Moreover, we don't want the trivial protocol where everybody just broadcasts their 2 to the m length lookup table to everybody else. We'd like a protocol with polynomial communication in m and n, or certainly at least sub-exponential communication. Notice that's a very strong requirement, polynomial communication, because I have an exponential number of things in my head I might potentially like to tell all of the other players. So the question is, how well can you do if everybody can only communicate a vanishingly small fraction of what they in principle have to say? All right, so that's going to be, so when I say a polynomial cost communication protocol, I just mean this protocol for exchanging bits among the players, where the number of bits passed around is polynomial. Okay, and that's another object that we have a lot of experience proving lower bounds against. All right, so in routing games, I talked about how it's important to parameterize by the class of cost functions, and that the price of entropy will depend on the class of cost functions. And there is an analog of that for control auctions. Again, control auctions we usually parameterize by something. Here, it's going to be the class of allowable agent valuations. Okay? So you could look at the super general class, just like arbitrary monotone set functions, or you could look at a very restrictive class, like say just additive valuations. And in general, when we get to games, the price of anarchy will depend on how big the valuation class is. Obviously, the price of anarchy will only be worse the more valuation classes that you allow. Okay? For this talk, I don't want to really get into this kind of hierarchy. I just want to sort of pluck out one particular class to focus on. And we're going to look, just for the talk, we're going to look at the case of subadditive valuations. So we assume that each agent's set function, each agent's VI, is subadditive, which means exactly what you would think it would mean. It just means your value for the union of 2 bundles is at most the sum of your values for each bundle separately. Okay, so this is going to be the last part of the problem. Okay, subadditive valuations, though again, the methodology makes sense for other classes as well. Okay, so that's our optimization problem. Approximately maximize welfare when bidders have subadditive valuations in this sort of multi-party communication model. Okay, that's the optimization problem. What's the game? Okay, well, I want to connect hardness results for communication protocols to the price of anarchy of which game? We're going to be looking at games induced by simple mechanisms. So I'll define for you what I mean by a simple mechanism in a couple slides when I actually need it. To sort of warm up, let me just tell you about one specific way, one specific selling procedure you could use in this setting that I hope you agree seems relatively simple. Okay? And then we'll be precise about the sense in which it's simple in a couple slides. So let's look at simultaneous first price auctions. Okay, so we have these M items for sale. Bidders have preferences. Suppose we ask bidders a little bit about their preferences for items, in that we solicit a bid from each player for each item. Okay? So each player submits M numbers to the selling procedure, a bid for each of the items. We now decide on an allocation of the items by using a standard single item, first price single item auction for each of the items. So you run M of them in parallel. So there's one first price auction for item number 1. You look at everybody's bids on item number 1. Whoever bid the highest on that item wins it, and they pay whatever they bid. Item number 2, you look at who's the highest bidder on 2. That's the winner. They pay what they bid, etc. Okay. So that's a simultaneous first price auction. Everybody submits M bids. They're sold separately using to the highest bidder at their bid. Okay, so this is now a game that we've specified, right? So the players of our game are just the N bidders. The strategies of the game are induced by the choice of mechanism. So the strategy space is just going to be all possible ways you could bid in a simultaneous first price auction. And the payoff of a player is going to be their sort of net utility. So the value of the items that they receive minus what they have to pay for them. So all of the agents, we will assume, will bid in order to maximize that utility function. Value of what they get minus what they have to pay for. Okay? So those are the 3 ingredients of the game: player, strategies, payoffs. So we can now actually talk about the Nash equilibria of that game. And in particular, we can talk about the price of anarchy of the game induced by this simple mechanism. Okay? And so now, just to sort of keep the price of anarchy, at least 1, I'm going to switch it so that the maximum possible welfare is on top and the worst case equilibrium welfare is on bottom. Okay, so again, the closer this is to 1, the better. Okay. All right. Questions? So I'll give you this as one example of the type of game I'm interested in around combinatorial auctions. Okay. Good news. Okay? Just like this community has completely nailed the price of anarchy of congestion games, it's also completely nailed the price of anarchy of simultaneous first price auctions. I'm going to list here specifically the results for bidders with subadditive valuations. Okay? So there's 2 different papers, one an upper bound, one a lower bound, both great papers that give matching bounds. The price of anarchy turns out to be exactly 2 in simultaneous first price auctions with subadditive valuations. The upper bound is from a paper by Brendan and co-authors, and that's a very interesting upper bound in that it provably goes beyond the smoothness arguments in a way I'm not going to have time to discuss, but it's a novel, sort of a certifiably novel type of upper bound. The lower bound is just a tour de force. It's very impressive by Georges and collaborators. It's again an explicit construction, and it's a pretty difficult explicit construction. So they just write down the valuations, subadditive valuations, they write down an equilibrium, and they say, look, this equilibrium has only 50% of the welfare of the maximum possible. Okay? So completely tight results. So that's pretty great. All right, so what then how could complexity theory help us, given that we already know the exact answer to this question? Well, simultaneous first price auctions are a supernatural format, so we absolutely want to sort of nail down the price of anarchy, no question about it. But also, most of us in this room are sort of algorithm designers, so we say, okay, could we do something better? Like, who says we have to use simultaneous first price auctions? What if we switch to second price auctions, or all pay auctions? Or what if we allow people to bid, not just on individual items, but also on pairs of items, for example? Could we do better than this factor of 2 with a more clever choice of auction format? Now, you have to be a little careful how you phrase this question, okay? Because the way I phrased it so far, the answer is, obviously, yes, we could do better. We could run what's known as the Vickrey-Clark-Groves, or VCG mechanism, wherein it's a dominant strategy for each bidder to reveal their entire valuation, and then at that dominant strategy equilibrium, the welfare is maximum. Okay, so it actually maximizes welfare at equilibrium, the VCG mechanism. Only problem is, remember, everybody's valuation is a lookup table of length 2 to the m. Okay, and the VCG mechanism asks everybody to report that entire table. Okay, so it's a direct revelation mechanism, and that's a lot of information. So the interesting question is, can we get better than a factor of 2 without resorting to the exponential communication used by the VCG or any other direct revolution mechanism? Okay, so that's going to be the question we're interested in. And so for the results, I'm actually going to be able to get away with a quite permissive definition of what I mean by a simple mechanism. I'm just going to need that the number of bidding parameters per bidder is sub-exponential in the number of items m. Okay? So in the VCG mechanism, remember, or any of the direct revelation mechanism, you basically ask each player for their bid for a bid on each of the 2 to the m possible bundles. So in the VCG mechanism, you have an exponential number of bidding parameters, so it does not qualify as simple. In simultaneous first price auctions, we only ask each bidder for m numbers, 1 for each item, so that would be a simple mechanism. If you allowed bidders to bid on pairs of items, not just single items, then you'd have roughly m squared bidding parameters. That again would certainly meet this definition of simple. Okay. So that's the question I want to study. Right? Could we do better than simultaneous first price auctions with a mechanism that is simple in the sense that it has a sub-exponential number of bidding parameters? Okay. And the answer is going to turn out to be no. And so that's going to follow from another one of these sort of translation theorems, which takes hardness results. In this case, it's not going to be for algorithms, it's going to be for protocols, and it translates hardness results from protocols to, this time, unconditional lower bounds on the price of anarchy. Okay? So there's going to be a bunch of words that show up here, but I sort of first wanted to show you how to think about this theorem before I show you the exact statement. Okay? So it's going to be a reduction, and if you want to prove lower bounds on equilibria, it suffices to prove lower bounds on a particular type of communication protocol for the underlying optimization problem. Okay? All right, so what's the fine print? So let me tell you, it's for both the hypothesis and the conclusion. So again, for the hypothesis, we want some hardness of approximation factor, so you can't distinguish between the max buffer being at least W star or at most some W star over alpha for some constant alpha. It's going to be important that the lower bound holds even for non-deterministic protocols. That just means, you can either think of it as protocols where the players can sort of guess what message to send next, or you can think of there being sort of a verifier who can help out the players by writing some advice on the blackboard. Anyways, non-deterministic protocols, that's a bigger class than deterministic, and so it's a stronger assumption that you have a lower bound against even non-deterministic protocols. And we'll see why that's important when we talk about the proof. Okay, so if you have such a lower bound, if you can show that non-deterministic protocols using a sub-exponential amount of communication cannot distinguish between maximum buffer at W star over alpha, the conclusion says then, for every single simple mechanism you could possibly use, it doesn't matter which one, if you look at the resulting class of games, ranging over all choices of bidders' valuation functions, the worst case price of anarchy over that family of games is going to be have the same lower bound. Okay, the price of anarchy will not be better than alpha, no matter which simple mechanism you use. One additional piece of fine print, this statement is actually not quite what I just said. It's a lower bound not against what you'd really want, mixed Nash equilibria, but only against epsilon approximate mixed Nash equilibria, where all of the best response conditions are satisfied up to epsilon. Notice there's only more approximate equilibria than exact equilibria, so it's a weaker statement to have a lower bound on the worst case approximate equilibrium than on the worst case exact equilibrium. Okay? The good news is the theorem is still true if epsilon is super small. It could be, say any inverse polynomial function of n and m. I don't know if the theorem is true when epsilon equals 0. I think that's an interesting open question. I just don't know. Okay? You'll see where the epsilon comes from when we talk about the proof. Okay? But because we can take epsilon so small, I kind of will gloss over that difference. Right. So that's the punchline. Okay, for combinatorial options, any lower bound against non-deterministic protocols translates to a price of anarchy lower bound for any simple mechanism you could use, any mechanism with a sub-exponential number of bidding parameters. Okay. So here, let me, yeah.
So, are you using demand queries, value queries, or just communication?
It's just the communication model. Yeah. Let's see. Yeah. And that's sort of important. Yeah. So if you had a lower bound only against demand queries, if you sort of weakened your hypothesis, I don't immediately see how you could get the proof to go through. Maybe you could, but I don't see it on the board. Yeah. Good. So let me show you an application first, and then I'll say a little bit about the proof. So again, this theorem would not be interesting unless we had examples where the hypothesis was true, unless we had examples of of lower bounds against non-deterministic communication protocols. And the good news is many smart people in algorithmic game theory have thought pretty hard, actually, about what communication protocols can and can't do for these welfare maximization problems. For example, for the running case of subadditive evaluations that we're talking about, Dobzhinsky, Nissan, and Shapira proved a lower bound of 2. Okay, so they showed that any sub-exponential cost communication protocol, even non-deterministic, cannot guarantee a welfare factor better than 2. This is exactly the kind of hypothesis you can plug into the general translation theorem on the previous slide. And so if you chain those two theorems together, you immediately find that for bidders with subadditive evaluations, no simple mechanism can have a worst case price of anarchy better than 2. Okay. So modulo this epsilon being 0 versus epsilon being very small, modulo the epsilon, this recovers the factor 2 lower bound on simultaneous first price auctions, not with an explicit construction, but rather using a reduction. But moreover, right, this lower bound is not just about simultaneous first price auctions, it's about literally any simple mechanism you might conceivably use. Which again, as a result, I have no idea how you would prove that without resorting to complexity theoretic techniques. Okay. So this actually shows a sense in which simultaneous first price auctions are an optimal simple mechanism for bidders with subadditive evaluations, in the sense that it minimizes the worst case price of anarchy over all simple mechanisms. All right, so that's an example application. Let me now say a little bit about the proof, and this will follow exactly what we saw in the first half of the talk. So again, what drives the results are guaranteed existence and efficient verifiability. Okay? So we're talking about mixed Nash equilibria, so we're not worried about guaranteed existence, we definitely have it. But actually there's an issue around the question of efficient verifiability. Because let's even think about like simultaneous first price auctions, this allegedly simple mechanism, where I submit one bid on each of the items. Okay? That means the number of actions available to me, the size of my strategy space, is exponential in M. Right? Like on each item independently, I can decide whether to bid 0 or 1. So that already gives me 2 to the M different options. Okay? Why is that a problem? Well, to even write down a Nash equilibrium, you need to write down a mixed strategy for each of the players, and if a mixed strategy has full support, that's one probability for every single one of the actions. And I just told you the number of actions, even in this case, is exponential. Okay? So forget about efficiently verifying an equilibrium. I can't even write down an equilibrium with a polynomial number of bits, or sub-exponential number of bits. Okay? So that's a technical difficulty that arises that we didn't have before. The action spaces are really big, and that causes problems for efficient verifiability. So how do we salvage things? Well, we rely on a famous theorem of Van Gus and collaborators, proving the guaranteed existence of small support approximate Nash equilibria. Okay, this is where the epsilon comes from. So if you go from exact Nash equilibria to epsilon Nash equilibria, all of a sudden, there's guaranteed to exist approximate equilibria where the dependence on the number of actions is only logarithmic. Okay, so n here is the number of actions in the game. All right? So in simultaneous first price auctions, where you have only an exponential number of actions, the support size you need to resort to is only polynomial in everything, okay, in the size of the game. All right? That's something we can write down in a polynomial number of bits, and also we can check that it is, in fact, an epsilon approximate Nash equilibrium efficient. Okay? So that's what's going to save us. Okay, so we're going to give up on exact Nash equilibria, we're going to focus to epsilon approximate Nash equilibria, we're going to use the Smart-Hawkes et al. Result to show guaranteed, to argue, to use the fact that there's guaranteed existence of small support equilibria. Okay, good. So now the proof works kind of exactly the same way as it did in the rounding game case. So again, we're going to assume we have a too good to be true price of anarchy bound. Okay, we're going to assume that, suppose it's 4 epsilon mixed Nash equilibria, price of anarchy is rho, strictly less than alpha. Here is the optimization problem, unsolvable by sub-exponential communication protocols, deciding whether the maximum alpha is at least W star or W star over alpha. And we're going to show that this too good to be true price of anarchy bound, actually, from it we can extract a too good to be true non-deterministic protocol, okay, that actually decides whether we're in case 1 or case 2. So it's going to work the same as before. What's the sort of succinct certificate that we're going to check? Well, so the certificate will just be provided in the form of a small support epsilon Nash equilibrium. Okay. By the LMM results, we have guaranteed existence. That was the whole point of that lemma on the last slide, guaranteed existence of small support equilibria, and then it's an easy exercise to show you have the efficient verifiability that you need. Okay. So that's the form of the certificate. What do you do with the certificate? You compute, you verify it's an equilibrium, an epsilon equilibrium. You compute the expected welfare of this epsilon equilibrium, and you see whether this equilibrium has high or low welfare. Okay? If the welfare is high, this again is sort of the obvious case, right? So certainly if the equilibrium welfare is bigger than W star over alpha, then so is the optimal welfare. So we can't be in case 2, we have to be in case 1. Okay, that's not surprising. Where the price of anarchy bound is used is in the other case. So we can be convinced that the maximum possible welfare is small just if this equilibrium itself has very low welfare. Okay? So if the equilibrium has expected welfare less than at most W star over alpha, then by virtue of the price of anarchy being merely rho less than alpha, we can conclude that even the optimal allocation has welfare at most rho over alpha W star. That's strictly less than W star, so this convinces us that we're in case 2. This is a non-deterministic protocol for this decision problem, which by assumption does not exist. All right. So let me wrap up, maybe just with one open question, but it is a super juicy open question. So I would really love to see progress on that. So one of the main kind of punchlines of the second half of the talk was that there's a sense in which simultaneous first price auctions are an optimal simple mechanism. So specifically, we were looking at bidders with sub-additive valuations. We proved an upper bound on the price of anarchy of 2 for simultaneous first price auctions, and a lower bound of 2 on every possible simple mechanism. Okay, that's the sense in which it was optimal for bidders with sub-additive valuations. We do not know whether the same auction format, simultaneous first price auctions, are an optimal simple mechanism for other natural choices of valuation functions. For example, we could look at the case of submodular bidder valuations. Okay, this is where you have diminishing returns and additional items. This is a stronger assumption. Okay, this is a more restrictive class than sub-additive valuations. So the price of anarchy is only going to get better, okay, because it's a special case. All right? And actually, we do know exactly what the price of anarchy is of simultaneous first price auctions. It turns out to be exactly 1 minus 1 over E. Okay, so the positive result here comes from a result of Sertanis and Tardosh. The lower bound is from the same paper that proved the lower bound of 2 for the sub-additive case. Right? So that's not the question. The question is not what is the price of anarchy of this one fundamental mechanism. The question is there anything better that's also simple? Okay? So based on what I've told you today, your immediate reaction would be like, oh, well, I guess all I need to do is prove a communication lower bound of 1 minus 1 over E, and then we'll be done. Okay, then we'll prove that simultaneous first price auctions are an optimal simple mechanism. Okay? There's one problem, which is that it's actually false that there's a lower bound of 1 minus 1 over E for communication protocols with sub-additive evaluations. There's a fairly old now paper of Figa and Vondrak where they give a communication protocol for welfare maximization that does better than 1 minus 1 over E. Only by something like 10 to the minus 6th, but it does do better than 1 minus 1 over E. Okay? So that means the communication framework, so if it is the case that simultaneous first price auctions are optimal for sub-additive evaluations, the framework I just showed you is inadequate to prove it. Okay? The framework I showed you is adequate to prove weaker lower bounds. So for example, there's a communication lower bound of Dobzhinsky and Vondrak, which implies you can't do better than 77%. But in between that, we don't know. Okay? There's a gap between 63 and 77% of what you could achieve with a simple mechanism. There's 2 possible outcomes of this open question. Both would be super interesting. Okay? Outcome 1 would be that simultaneous first price auctions are in fact optimal simple mechanisms with submodular valuations. That would force you to develop a stronger lower bound technique. So that would be interesting. Alternatively, maybe there's some other clever choice of mechanism that actually gets you a price of anarchy bound better than 63%. That obviously would also be extremely interesting. So that's what I have to say. So thanks very much.
Thanks a lot. There is time for questions.
So it's always poly communication, but what if you insist on strictly less than poly, say linear communication, or something that's much smaller?
So the question is, what if you restrict the class of protocols against which you have a lower bound, right? So you want, so the hypothesis in the translation theorem said, suppose you have a lower bound against all poly communication protocols. And I believe the question is, what if you only had a lower bound against a restricted class of communication protocols, like linear protocols? Yeah, so I think what would happen is you would rule out simple mechanisms that have exponential size action spaces, but not action spaces that are a little bit bigger than exponential. And so it's a weaker hypothesis, you expect a weaker result. So I think you get a lower bound only. So basically what happens is the communication used by the protocol, sort of that, raised to the 2 winds up being roughly the action, the size of the strategy space you can handle. So yeah, I think that's the answer. It would give you, so like for example, a lower bound against linear communication protocols would not rule out simple mechanisms with like 2 to the square root of m bitting parameters doing really well.
Yeah, if I wanted to do away with the epsilon in the second result, I just want to double check, would it be enough to show just the existence of a small support equilibrium for games in that class?
Yes.
Run a validation class?
Yep.
Yeah. Do we know that's not the case, or is that the counter-logic?
Yeah, that's a good question. So Brendan's asking about basically the tightness of the LMM result, and whether you can get rid of the epsilon. Certainly in general games, we know that the dependence is optimal on both the number of actions and on epsilon. As Brendan points out, these are special games and you might hope for a stronger result. I am not aware of any work in either direction on the question. And one thing Brendan pointed out, which is absolutely correct, is if you wanted to remove the epsilon in the second theorem, it would be enough to prove an analog of LMM without the epsilon for this particular class of games, which for all I know is true. So, yeah, great question.
So does this complexity framework allow you to generalize POA results to other definitions of social welfare functions?
Good. So the question is, what is the role of the social welfare assumption? Or you could ask the same question about, in rounding games, how much is this about the joint cost objective? And it's actually not at all. Okay, so this is very different than, say, the theory of smoothness proofs, which is kind of tailored toward welfare maximization type objectives. Here, all you need is this hardness of approximation result, right? So changing the objective will change the hardness of approximation of the underlying optimization problem, so it'll change what lower bounds you get. But the methodology applies equally well. Yeah, good question.
Another question is, okay, there are some modular evaluations that do not require communication, but still they have hardness approximation.
Right, right.
Does this framework say something for this case?
Good question. So the question here, so you'll notice I sort of took 2 different tacks in the 2 parts of the talk. The first talk, I was looking at routing games which have a succinct description. So you can talk about the computational complexity of the optimization problem. In the second part, I instead worked in this sort of multi-party communication model, where you don't have a succinct description of the evaluations, rather they're in everybody's heads. Okay? But you can mix and match these however you want. So for example, in the welfare maximization section, you could say, well, let's go back to a Turing machine type model. Let's just assume that each bidder has a succinctly described submodular valuation, which with an efficient value oracle. So, budgeted additive valuation, say, or something like this. So then again, that could change the hardness of approximation result, but whatever NP hardness of approximation result you prove for that class of succinctly described valuations, that's going to translate into a lower bound on the price of anarchy for that same class, although now with a complexity assumption.
So now the assumption is NP, not equal.
To co-NP, yeah. So if you're in the Turing machine model, right, because we basically don't have any unconditional lower bounds, in computational complexity, we get only conditional lower bounds in the price of anarchy. In communication complexity, we do have unconditional lower bounds, so you get unconditional lower bounds on the price of anarchy in exchange.
Okay, well, let's thank him again.
Okay, thanks.